In our final lesson on relationships, we are going to investigate first differences. Our learning goals for this lesson is to calculate first differences and then use the first differences to determine if a relationship is linear or non-linear. So to begin with in this lesson, we have a series of squares and we're given the lengths of each one. So each square grows by 1 centimeter of side length. So 1, 2, 3, 4, 5 centimeters. In our first table, we are told that we have side length 1, 2, 3, 4, 5 as above, and we want to calculate the perimeter. Well, if you recall, perimeter is just adding the lengths around the side of the square. So in the first square, we have 1 plus 1 plus 1 plus 1, so the perimeter is 4. Another way of doing this is to use the fact that we have 4 sides of equal length 1, so we can go 4 times 1, which is 4 centimeters. In the second square, we have 4 side lengths of length 2, so we can do 4 times 2, or we can add 2 plus 2 plus 2 plus 2, which is 8. In the third square, we have 4 sides of length 3, so 4 times 3 is 12, or you can add all the 3's together and you get 12. In the next square, we have 4 side lengths of length 4, so adding them together or going 4 times 4, you get 16 is the perimeter. And in the final square, we have 4 sides that have a length of 5, so 5 times 4 is 20, so the perimeter is 20. So we now have our x values in the first column and our y values in the second column. So side length is our independent variable, and the perimeter is our dependent variable, because the perimeter depends on how long the side length is of the square. So let's plot these points. So my x-axis, I have to go from 1 to 5. So I'm going to go up in ones. And my y-axis, I have to go up until 20. So that's 2, 4, 6, 8, 10, 12, 14. Doesn't work. So let's try 4s. 4, 8, 12, 16, 20. That looks like the best scale to go up by 4s. And let's label our axes. The side length. The units are centimeters. And my y-axis is the perimeter. And my unit is centimeters again. So now let's plot each point. So 1, 4, 2, 8, 3, 12, 4, 16, and 5, 20. So I get points, and it's pretty clear that they form a straight line, a perfect straight line. The trend line goes through all of those points, or the line of best fit goes through all of those points. So we can say that this is a linear relationship. And that's the goal for this lesson, is to figure out if this relationship is linear or nonlinear. We could go into more detail and say this is an increasing linear relationship, meaning as the side length increases, the perimeter increases. But I'm just interested if this is a linear or nonlinear relationship. So the one thing that we haven't talked about, which is new in this lesson, is calculating the first differences. When finding the first differences, we want to know how our y values are changing. So to go from the first y to the second y value, and then the second y value to the third y value, and so on. So to go from our first y value to our second y value, or in this case, first perimeter to the second perimeter, we're jumping by 4. We're going from 4 to 8. So You can easily see in your head that you're adding 4, but sometimes these numbers won't be as easy, so it's good to take the second number and subtract the first number. So this is what you're doing in your head, but it is worth writing down here. So you're taking your second y value, subtract your first y value. And then to get your next second difference, you're taking the next y value, your third y value, and subtracting your second y value. So 12 take away 8, which is 4. Again. And then your next first difference, you're finding the difference from the next step, from your third y value to your fourth y value. And again, you can see the difference is 4. And we can show that by going 16 take away 12 is 4. And then finally, your last first difference is going from your fourth y value to your fifth y value. So 20 take away 16 is 4. So we notice that all the first differences are the same. They are all equal to 4. This value of 4 is significant, and we are going to go into a lot more detail about this value in our next topic. A couple things you should note is that the side length, or our x values, always went up in 1, and that's important. So it went from 1 to 2 to 3 to 4 to 5. You're always jumping up by positive 1. So the first differences are important, and we can calculate them, but only when the x values go up by 1. And another thing we should talk about very quickly is that there's something called second differences, which is the difference of your differences, and you're going to do that more next year in grade 10. So let's go to our next table. In this one, we want to calculate the area of each of those squares. So to remind you, the first square had a side length of 1. Area is length times width. The length is 1, the width is 1, so the area is 1 centimeter squared. When the side length is 2, the length and the width are each 2, so the area is 2 times 2, which is 4. And then when the side length is 3, to get the area, we do 3 times 3, which is 9. And then when the side length is 4, 4 times 4 is 16. And when it's 5, 5 times 5 is 25. So the y values are how the area changes as the side length increases by 1. So let's plot this. My side lengths, again, I'm just going to go up by 1s. Remember to label your axis. So this side, my y-axis is area in centimeters squared. And I need to go up to 25. So let's see, 4, 8, 12, 16, 20, 24, 28. So again, I'm going to go up in 4s. So let's plot the points. 1, 1 is going to be down here. 2, 4 is up here. 3, 9. 4, 16. And 5, 25. So if you look at these points and the trends, a line of best fit is not as appropriate as a curve of best fit. And if you notice, the curve can go through all of the points that I plotted. So now let's go and calculate the first differences. And again, the first differences are just what jump are you making between each step of your y values. And again, notice that my x values are going up by 1. So I only calculate first differences when my x values go up by 1. So from 1 to 4, I jump by 3, and the calculation is 4 minus 1 is 3. From 4 to 9, the jump is 5. From 9 to 16, the jump is 7. And from 16 to 25, the jump is 9. So if you take a look at your first differences here, they're all different. And we already said we drew a curve of best fit as opposed to a line of best fit, which means this is a non-linear relationship. So we can conclude that when the first differences are different, there is a non-linear relationship. And in the above table, when the first differences are the same, we see that there is a linear relationship. So there are two ways to be able to tell if a relationship is linear or nonlinear. The first way is to graph and see if the points form a line or a curve. And the second way is to look at the first differences. If they are the same, it is a linear relationship. If they are different, it is a nonlinear relationship. It is probably more easier to see or more mathematical to calculate the first differences, because sometimes if you have points, it's hard to see if they form a straight line or a curve, especially if you only have a few points. And again, as I mentioned, in grade 10 you will start investigating the second differences, but you might be able to see what the second differences are here. And it's just the jump or the difference of your first differences. And you can see here we go from 3 to 5, so we're adding 2, 5 to 7 adding 2, and 7 to 9 adding 2. And we notice that all the second differences are the same. And that's a very interesting property that you will look at in grade 10.